This problem is called Try Your Best, and we'll be working with tries. The first question is, what strings are stored in the try shown? So you can take a moment and think about it. And the words stored here are going to be inch. So starting at I and going up to, or this like valid word start and going to the word end, highlighted green, as well as index, as well as info. And so again, we're always starting from a valid starting letter going to a word end. And those are the strings stored. The second part asks, now insert the strings indent, inches, and try into the try. So again, you can take a moment and think about this. And so the first thing we're going to do is insert indent, right? And so we're going to start and we're going to go, okay, is the letter I already in here? Yep. And then N and D. Yep. And then E. Yep. And then do we have an N next for indent? And there's not, right? So that means we have to start adding new nodes to our try. And so we're going to go, okay, we'll add the N and then we'll add the T. And so the end result is something like this. We have another word end for T because it's signifying we had this word indent that was just inserted. And so the great thing about this you're going to notice is that we didn't have to insert a bunch of new characters to add indent. We only inserted nodes representing N and T. And so this is hopefully showing you some of the advantages of using a try, is that we are reusing this space in a way. Now we're going to move on to adding inches. So again, take a moment and think about this. And you're going to see we go through letter by letter, seeing if they're already present. And we see I and C, H, but there is no E. So we're going to have to go add the E and then the S. And the end result looks something like this. Again, we've added another word end hanging off. And so here we both have the word inch as well as inches. Lastly, we're going to add try. So take a moment and think about it. This one's a little more interesting because unlike all the other words so far in the tree, which start with I, we're actually starting with the letter T. But it's simple enough in a try. All we have to do is just add another valid starting letter. And so we'll do something like this. And that is all of 1A. Now we're going to do problem 1B. What is the runtime to find out if a given string is in the tree? And what is the runtime to add a string to the tree? Describe these answers in terms of n, the number of words in the try. I've realized this is a typo. We should be saying try. You may assume the max length of any word in the try is a constant. Take a moment to think about this one. So for the first part, just finding out if the given string is in the tree, let's go through an example, right? Let's say we're looking for the word indent. And so all we have to do at the start is just look at the first letter and go, okay, is that here? Is there like a valid path that we can take that has that first letter? Yep. And then we'll look at the next letter and see, okay, is there another node for that letter? And then we'll look at the next letter and the next letter and so on and so forth until we reach the end of the word. And then we just verify that it's a word end or a node that's colored green. And so all the time that takes is the length of the word. Notice that we're not wasting our time looking at other nodes in the tree that aren't in our word. So it doesn't matter how many other words are in our try. There could be a million other words in the try, but we go straight to the point, straight to the path we're looking for. And so it doesn't matter how many words are in there. It's going to be only related to the length of our word. And we've assumed that the max length of any word in the tree is a try is a constant, which means this operation is constant time. And this is a common assumption we make, that the max length of any word in a try is constant, just because at the end of the day, in the English language, I think the longest word is probably not more than like, I don't know, 30 letters. That could be false, but like most of the words we use are not that long, right? And so we can sort of treat that as a constant. And so that is one assumption we commonly make, but not always make. Otherwise, we could say that maybe if the max length of any word in the tree was K, then this would be, big O of K time. The second part asks, what is the runtime to add a string to the try? And so we can take a moment and think about this one again. And let's say we wanted to add the word smile, because it's a beautiful day, right? And so all we have to do here is see if the letter S is already in there and it's not, and then we would just add nodes letter by letter. And so again, this only takes as much time as the length of our word. Alternatively, if let's say we wanted to add the word tries, right? Well, still, the word try might be in our tree, but then all we have to do is go letter by letter and check if it's already there. If it's not, then we'll add the new letter. And so basically all we do is we go letter by letter, see if we already have the correct node there, and if we don't, we add it. And again, this is just proportional to the size of our word. But we've said the size of our words are constant, therefore the runtime to add a string to the try is also constant. And so this is problem 1b. Lastly, how could you modify a try so that you can efficiently determine the number of words with a specific prefix in the try? Describe the runtime of your solution. This is a pretty interesting problem, so you can take a moment and think about it. And now let's remember that our underlying implementation of a try is totally up to us, right? We could add any sort of metadata to these little node objects that we have, right? We can add whatever the heck we want. And so we could imagine maybe we're going to say associated with each node is the number of words beneath it. What does this mean? Well, for example, there's only one word in this whole area, right? So these just have one word beneath them. But what about the letter I? Well, there's 1, 2, 3, 4, 5. So we'll just associate a number with this node. Similarly, N has 5 beneath it. C has 2 word ends beneath it, or in its like children in the try. D has also 2, and F has 1. And so we can see that we're associating a number with each node. And the way we would implement this in practice, for example, is that every time we add a word, you're going to recall that the way we add, as we just described, is going along and at each node, either checking if the node is there or adding it if it's not. And so in the process, every node that we either check or create, we're going to increment its count. So for example, if let's say we currently look like this, and all of these have 1 associated with them, and I'll make this look a little neater. Now let's say I wanted to add the word tree, like T-R-E-E. Well, I'll start and I'll go, okay, is the letter T there? Yep, and it is. And so I'm going to actually increment the count there as I'm going along and traversing the try. Then I'll say, okay, is the letter R here? Yep, and we're going to increment this. Then I'll say, is the letter E here? And it's not. So I'm going to make a new one and just either initialize it with the value of 0 and then increment it the same as we're incrementing these, or just start at 1, right? And then again, I'm going to make a new one. And so it would look something like this. And then if I wanted to add trees, also this should be highlighted. If I wanted to add trees, then I would again go, okay, we'll increment this because we're adding another word as we go along. And we go, okay, increment this. And we increment this. I'm just gonna scribble over. And then we add S. And this starts at 1. All of our new nodes start at 1. And so in this way, we've modified our try. Oops. We've modified our try to efficiently determine the number of words with a specific prefix in the try. And what's the runtime of our solution? Well, let's say we wanted to know how many words in our tree started with TR. Well, then we'd just simply go and we'd first look at the first letter in our prefix, which is T, then look at the next one. And at that point, we've determined the value at this last word or letter in our prefix is the number of things beneath this entire prefix that start with this. And so it would be 3. On the other hand, if we wanted to find out how many words started with the prefix TRI, again, we'd go down and we go, okay, we're at T, now we're at R, and we're at I. And the count here is how many words start with the whole prefix TRI. And that's only 1. And as a final example, if we wanted to see how many words start with INDE, right? We'd assume that there's some count here. And we'd simply look going all the way down our little thing and take the number associated with the last letter in our prefix to be the number of words starting with that prefix. And so again, just like as we said earlier, this is going to be a constant time operation if we assume that the max length of any word in our trie is constant. And so this is constant time to determine how many words start with that prefix.